This lecture is over covalent bonding and it's titled Sharing is Caring. It says sharing is sometimes more demanding than giving, and you've got Mary Catherine Bateson right there. So, what we want to do is we want to look at our learning goals, and our learning goals are that you understand the nature of a covalent bond. Now, a covalent bond is going to be quite a bit different than an ionic bond, and because it's quite a bit different, it's also going to have very different properties that we're going to look at. So, students, you should be able to distinguish between not only covalent and ionic, but within covalent bonds, you should be able to distinguish between what's called a polar and a nonpolar bond. These are very different as well, and we'll talk about what makes a polar and what makes a nonpolar bond. You should also be able to move from the name to the chemical formula and the chemical formula to the name for covalent compounds as well. It's very similar to ionic bonding, but it is a little bit different, so we need to make sure we go over the rules. Okay, so first of all is a covalent bond. We learned last time that ionic bonds are formed when you actually take an electron and you remove an electron from one side to the other. Okay, so this thing right here gains an electron, it becomes negative. This one lost an electron, so it becomes positive. And then the attraction between the positive and negative is what's called an ionic bond. A covalent bond's a little bit different. What it is it says we've got a pair of electrons that are you can think of it almost like an ice cream sundae here, and it's being shared between these two atoms, where this one thinks it's getting those two electrons, and this one thinks it's getting those two electrons. So because of that, you have this covalent bond that's a series of shared electrons between two atoms. So, in order to look at covalent bonds, one of the first things we need to do is we need to review electronegativity. We covered electronegativity earlier this year, and we said basically it's the measure, it's how much an electron or an atom wants an electron. And we said there's a couple of things that it depends on. It depends on the distance from the nucleus, so the distance between the protons and the valence electrons. It also depended on the number of protons, and it also depended on the stability of the ions. And as a result, we said that electronegativity increases as you move up the periodic table because you have more access, you get closer and closer to that nucleus. And it increases as you go across the periodic table because you have less what are called shielding electrons. But basically, what this means is electronegativity has the atom with the greatest electronegativity is fluorine. Okay, we exclude noble gases from these because remember, noble gases, they're happy, they don't want any electrons. So instead, the most electronegative element is fluorine. The least electronegative element would be cesium down here because it doesn't want an electron, it wants to get rid of its electron as much as possible. So now that we've taken a look at electronegativity, we can go back to our idea of covalent bonds. Covalent bonds always occur between two nonmetals. Okay, remember, whenever we have nonmetals, we're looking at something on the periodic table that is to the side of this particular step ladder right here. So it's to the right of boron, silicon, arsenic, and tellurium. It's this group 14, 15, 16, 17, and to some extent 18, although we won't talk about those in this case. So covalent bonds are formed between two nonmetals, so the right side of the periodic table. The molecules have a defined shape. So in other words, it will be a triangular shape, or it will be a tetrahedral shape, or it will be a linear shape, unlike an ionic compound, which kind of has a diffuse shape and it can change relatively easily. Whereas ionic bonds tend to be solids at room temperature, covalent bonds tend to be gases or liquids at room temperature. Covalent bonds have a low melting point. Contrast that with ionic bonds, which have a high melting point, and they have a very low boiling point as well. Contrast that with ionic bonds, which have a high boiling point. So if you look, the ionic and covalent bonds are kind of opposites of one another. One has low, one has high. One has a defined shape and one doesn't. You need to know to be able to distinguish between the covalent bonds and the ionic bonds. So the first thing we have, it says covalent bonds have a much lower melting point than an ionic bond. And it says, using Coulomb's law, explain why. And so we need to get into a little bit more about what a covalent bond is. But basically, what you have is you have two atoms that are sharing an electron. Now, I've drawn them as just atoms. Those aren't oxygens, but we'll just say, oh, we can say they're oxygens for this particular case. Or actually, we won't. We'll say it's atoms A and B. Okay, atom A wants these two electrons, and atom B wants these two electrons. Well, it turns out atom A could have a slightly bigger pull on these electrons than atom A, than atom B. So as a result, these electrons tend to gravitate towards atom A. When they gravitate towards atom A, we say that it is partially negative. And that's what this symbol right here means. It's kind of a Greek letter, but it means partial. And then you also have here, well, the electron is kind of moved away from this B, so we say it has a partial positive charge. Now, if you look, you have a partial positive charge and partial negative charge, and we know from Coulomb's law that these opposite charges will attract. So, if you have this opposite charges that attract, it should be similar to an ionic compound, but the difference is the fact that it is a partial positive and a partial negative. Because of that, it's not as big as when you have an ionic one, which is a full positive and a full negative charge. These two are going to be attracted to each other more strongly because they are complete charges. Okay, this is just a partial charge. It could be something like 0.001 charges. But as a result of that, there is a small attraction. So using Coulomb's law, we can say because the charges are greater in ionic bonds, then the attraction between the two is greater. So draw what happens to the electrons in a covalent bond between chlorine molecules. So the first thing you would realize is these two chlorines, they want to share an electron because this one right here has 7 electrons and this one has 7 electrons. And what they would like to do is they would like to each have 8 electrons. So what they're going to do is this chlorine's going to kind of offer this electron over here, and it's going to kind of go in between the two. And this chlorine atom is going to offer this electron to kind of go between the two. And what results is you have chlorine, and you still have your 1, 2, 3, 4, 5, 6. And you have chlorine. You have your 1, 2, 3, 4, 5, 6. And then you have 2 electrons that are in the middle. And those 2 electrons that are in the middle are actually what we call the covalent bond. What you see is this chlorine thinks it's happy because it thinks it has 8 electrons. This chlorine right here is happy because it thinks it has 8 electrons, even though they're sharing these two in the middle. Okay, these right here represent what we call the covalent bond. So we can share these electrons equally between two atoms, where they're each pulling with an equal amount, and they're sharing those electrons kind of right in between them. That's one of the things that we can do whenever we share electrons between two atoms. This right here, when you share electrons equally, is actually called a non-polar covalent bond. And what that means is because there's equal pull, you're not creating a partial positive or a partial negative. You're not doing that. It will happen occasionally because of chance or random movement of electrons, but all in all, the element doesn't have a partial positive or a partial negative charge. Because of that, this is an extremely weak bond. Okay, these things tend to be gases at room temperature, and they're not held together very well at all. The shared electrons happen between two atoms that pull equivalently. Now, the most common nonpolar bonds are what we call the diatomics. And a diatomic is one in which you have two of the same atom bonded together. So the example we have here is chlorine, which is a diatomic. You also have things like fluorine. You have things like oxygen. You have things like nitrogen. All of those represent what we call nonpolar covalent bonds because they are diatomic. It is also possible that you can have what is very, very close to a nonpolar covalent bond if two atoms are very close in their electronegativity values. So what you need to do whenever you're trying to determine if an atom has a nonpolar covalent bond is you look at the periodic table and you look at the electronegativity values. If you look over here to the right, in group 16, you have oxygen, which has a value of 3.44. In order to see if there's a nonpolar covalent bond that goes with it, you look for something that's around 3.4 as well. And if you look, there's actually nothing that's close to 3.4. But nitrogen at 3.04 is very similar to bromine at 2.96. Yes, they're a little bit off in terms of they're not exactly the same, but they're both very close to 3. So as a result of that, you could say that nitrogen and bromine would form something very similar to a nonpolar covalent bond. Now, if you share electrons equally, you can also share electrons unequally, in which one atom pulls the electron a little bit more. You have this famous quote from Animal Farm, says all animals are equal. but some are more equal than others, and you can say replace animals with atoms. All atoms are equal, but some atoms are more equal than others in terms of the electrons. So the shared electrons tend to gravitate towards one atom or another, and that's what you get here when we talk about polar covalent bonds. What you see here is this is oxygen and hydrogen, and these two are sharing these two electrons. But if you look, the electrons have gravitated towards the oxygen. The reason why is oxygen has a higher electronegativity value. Same thing happens over here. These should be here in the middle shared equally, but they're not. They tend to gravitate towards the oxygen. As a result, oxygen has what we call a partial negative charge, while the hydrogen has a partial positive on both sides. And that's because hydrogen has a lower electronegativity value. And we can go to our periodic table and we can say, okay, hydrogen's in the top left corner, it's 2.2. Oxygen's over here in group 16, it's 3.44. And as a result of that, what we can say is, all right, since this is the case, there's a difference of 1.2, and that's a pretty significant difference. So we can say that that right there is what we call a polar covalent bond. Here's an example. It says, using your periodic table with electronegativity, determine an element that will form a nonpolar covalent bond with nitrogen. And so we look at our periodic table and we say, okay, there's nitrogen. Nitrogen's in group 15, it's element number 7. It has a value of 3.04, and the closest thing that we have would be probably bromine. Now, krypton does have a small electronegativity that's there, it's at 3. It tends to be excluded for the most part because it's a noble gas, so I would say that the best bet in this case would probably be bromine at 2.96. In this example, it says the carbon-hydrogen bond is the basis for life as we know it. Describe the type of bond formed between carbon and hydrogen using your periodic table of electronegativities. So we go back to our periodic table of electronegativities. Remember, we're using p-table for those of you who couldn't remember where we got here. And if you look, hydrogen is in the top left corner. It has a value of 2.2, and carbon has a value of 2.55. So that is going to be a slightly polar bond because there's a difference of 0.3. It is getting pretty close to where it could almost be considered nonpolar, but it is still a difference of 0.3. So we do still say that this is actually a slightly polar covalent bond. So the degree of polarity actually matters. If something has a difference of like 1.2, it's going to be a very polar covalent bond. If it's something like carbon-hydrogen where it's a difference of 0.3, it is a slightly polar covalent bond. So you should be able to rank the polarity of various sets of bonds and say, yes, this one is more polar than this one. For any sort of quiz. Okay, so now we come to covalent compound naming. It becomes really important that you identify or you know the rules associated with naming covalent compounds and you be able to apply them into situations that you haven't quite seen before. And the first thing is you need to be able to identify the first element in the compound. And what you do is you move from left to right across the periodic table. The only difference with that left to right across the periodic table is that actually hydrogen fits in between nitrogen and oxygen. And that's kind of a weird, archaic rule. There is a reason for it. If we look at the periodic table, as far as nitrogen and carbon, that tends to be where it would fit if you're looking at it in terms of bonding order and those sorts of things. So that's why we tend to put it there, but you do need to know that that is where it goes. So the first element is the one that's furthest left, with the exception of hydrogen. And then the next thing you need to do is you need to be able to determine a prefix if necessary. Now, if there's a prefix, we do not put mono with the first element. If there is only one atom there, for example, if I have this right here, the first element is carbon, okay, I would call it carbon, not monocarbon, okay? So there is no prefix if there's only one thing for the first element. Now, if there's two, if you have something like C2O4, you could say, yes, C2O4, that means, well, that's not a great example, but if it's C2O4, you could say it's dicarbon, okay? But in this case, that's not what we have. So we've determined if a prefix is necessary. The next thing is we identify the second element. The second element in our case is oxygen. We need to determine if there is a prefix necessary. There is always going to be a prefix associated with the second element. So, since I have one oxygen, it would be mono, because there's one. You have mono, di, tri, tetra, petra, hexa, hepta, octa, nona, and deca. You do need to know these. Okay, you can't. I mean, you have to memorize them at this point. It goes in order. You should be able to do that relatively easily. Then you write the name of the element, monox, and then what it tells you to do is you replace the ending of the second element with "ide." And this takes a little bit of practice more than anything. So this is actually carbon monoxide. You replace the igen with "ide." And it takes practice more so than anything. There's no hard and fast rules. The easiest one are the halogens because it's chloride, fluoride, bromide, but it gets a little bit trickier when you're talking about other things. So as we work with them, you'll start to see kind of where you place the "ide." So here's an example. It says the molecule CH4 forms a tetrahedral shape as shown. We'll talk a little bit more about shapes later. It says determine whether the molecule as a whole is polar or nonpolar using the periodic table of electronegativities. So what we want to do is the first thing we want to do is we want to look at an individual carbon hydrogen bond. In order to determine whether that bond is polar or nonpolar, we consult our periodic table. We say, okay, hydrogen is 2.2. We say carbon is 2.55. And we say there's a difference of 0.35. In other words, the electrons are drawn towards the carbon. Well, in that case, you would think that this would be a polar bond in which you have a partial positive and you have a partial negative. Okay? But that's an individual bond. If you look at the shapes, though, you have this is pulling this way, this is pulling this way, this is pulling this way, and then that's pulling down. As a result of that, the net pull ends up being zero because of something called symmetry. It's a little bit hard to tell when it's in this tetrahedral shape, but if I draw it another way, it should be fairly evident. If you have it look like this, you can see that whenever I pull this way, I have a hydrogen to cancel me out. Whenever I pull this way, I have a hydrogen to cancel me out. As a result, the molecule as a whole is what we call nonpolar. Okay, since it's nonpolar as a whole, even though each individual bond is polar. So you need to be able to recognize situations in which you have polar bonds that turn into nonpolar whenever you put them together. And the key to that is symmetry, if you have something to cancel something out. It says name the following covalent compounds. So a lot of you go, oh, water, that's easy. Yes, that is technically the name for that, but there is a better name according to the formulas, and it is dihydrogen because I have two hydrogens, and then it is monoxide. So you have dihydrogen monoxide. Okay, you also have this right here, which we've already talked about, is carbon monoxide. Because remember, you don't want, monoxide, because you don't associate mono with the first element. Okay, it's only with the second element that you would put a mono. Next, it says write the chemical formula for these. So it says dinitrogen. So what I would do is I put nitrogen, and since it's di, there's two of them. And then pent means 5, and then oxide is oxygen. So dinitrogen pentoxide is N2O5. The next one is carbon tetrachloride. Okay, the first element is carbon. There's only one of them, and the reason why there's only one of them is there is no prefix. And then tetra means 4, so I have 4 chlorines. So you have carbon tetrachloride and dinitrogen pentoxide. Okay, metallic bonding is a special type of bonding that occurs between mostly transition metals. And what it is, it's a special type of electron sharing. Because these transition metals have what we call valence electrons in the d orbital, they tend to be delocalized. And what that means is the electrons are kind of shared between all of them. Okay, a lot of times it's called what we call a sea of electrons. It's it's kind of a poor analogy for what's going on, but because of the energy, the d orbitals, an electron in this atom could be shared with this one, or it could be over here, or it could be over here. In other words, there's no real way to define uh, who the electron belongs to. So it's sort of shared by the community, and we call that electron communism. It's one in which there is no ownership of a particular electron. Instead, it's kind of shared amongst all the protons that are there. Now, a couple of properties that deal with metallic bonding is the delocalized electrons allow electrons to move freely through it. In other words, because of that, an electron can come in, it can be transferred, it can go to the next one. And the reason for that is because of this delocalized shell. They're used to electrons coming in and out. As a result of that, most transition metals tend to be electrically conductive. In other words, they will allow electricity to flow through them. A second property is that they tend to be thermal conductors for the same reason. Because electrons can be moved through the atoms so easily, they can actually transfer energy to the atoms via the electrons as well, and so as a result, they tend to be thermal conductors. They also tend to, because they can slide past each other real easily in terms of the protons moving about in the sea of electrons, it tends to be easy to reshape these metallically bonded atoms, and so that results in these things being both malleable and ductile. Now remember, malleable means it can be pounded into very thin sheets, and ductile means it can be taken and drawn into very, very thin wires. So this example says, using the description of metallic bonding, explain why solid metallic bonds can change shape easier than solid ionic compounds. And the reason is it all has to do with the attraction between the positive and negative charges. Because this is such a great attraction between the two, it's very difficult to move these things away from each other and kind of create a smaller, thinner shape, or to pound them so that they separate because it's such a great attraction. Because of the delocalized nature of the electrons, if I take this proton and I move it over here, well, there's electrons over here to be able to make it stable. If I were to take it and move it over here, there's electrons over here to make it stable. What it does is it minimizes the repulsion between these two nuclei. They don't feel it as much because there's electrons in between that can kind of balance out that repulsion between the positive charges.